In this video, we're going to look at some applications using exponential and logarithmic functions. The growth in the total number of Starbucks locations each year can be modeled by this function given, where x is the number of years since 1970. We're going to predict the number of locations in 2018. All right, so in 2018, the year is going to be 48. So I have 0.307 times 48, which is going to be that exponent on the exponential base. So 0.2536 times e, which is second and then the division sign, raised to that exponent we just found. I suggest that you find the exponent separate just because if you forget to put a set of parentheses around it, it will alter the order of operations in the calculator and it's not going to read it correctly. So finding out what the exponent is first just saves you a little bit of a headache later. So I got 636,667.5785. So that means in 2018 there's about 636,668 Starbucks locations in 2018. Suppose that $2,000 is invested at 6% compounded semi-annually, so that's twice a year. How much money will there be after 5 years, and how long will it take for the money to double? So for this problem, we're going to need the compound interest formula, which we've used in the past. So A is the amount, it's equal to the principal times 1 plus the rate divided by the number of times we're compounding. And the exponent here is the number of times we're compounding times the total number of years that we're investing. So I have 2,000 as my principal times 1 plus 0.06 over 2 raised to the 2 times 5. I'm just going to simplify a little bit before I even do any calculations. I have 2,000 times 1.03 raised to the 10. And then just entering that into my calculator, I got 2,687.83, which means that after 5 years, there's $2,687.83 in the account. Now the second part of our question asks, how long is it going to take for the money to double? So the equation that I'm trying to solve here is when is that a value equal to 4,000? So 4,000 is equal to 2,000 times 1.03 to the 2 times t, because we don't know how long, we're looking for t. I divided both sides by that 2,000 so that I'm going to start getting t isolated. Now remember, when solving exponential equations, we use logarithms in order to solve them. So I'm going to take the natural log of both sides, which allows me to then use the power property and bring that 2t down. So I have the natural log of 2 is equal to 2t times the natural log of 1.03. Since it's all multiplication, 2 times t times the natural log, I'm going to divide by 2 times the natural log. That leaves me with the natural log of 2 divided by 2 times the natural log of 1.03. Now I want to show you how to enter that into the calculator if you haven't done this in a while. Natural log of 2, natural log is right next to the number 4, divided by, now since there's 2 operations in here, we have this division and then we have this multiplication, put that multiplication in parentheses. The other thing you could do is divide by the 2 first and then divide that whole thing by the natural log. So if you want to do it in 2 steps, you can do that, or just remember to put parentheses around it. When we hit enter, we get 11.72488, so on and so forth. So t is about 11.72, which means it takes almost 12 years for that money to double. The other way you can find this is using either the graph or the table. So if I go into y equals, the left-hand side of my equation I'm going to put into y1, and the right-hand side of my equation I'm going to put into y2. And it really doesn't matter which one you put into y1 or which one you put into y2. I just always do left into y1, right into y2. Again, since this exponent has 2 operations, please put it in parentheses so the calculator reads it correctly. Okay, thinking about a window, what do we want to see? Well, we know we're not going to see any negative x values, so I'm going to start my x min at 0, my x max. Doubling the money isn't an extremely large amount. We could say maybe 20 years, pretending like we have no idea how long it's going to take. And you could scale that by 1s or 2s. Now the y values, our minimum here is 2,000. It's what we're investing. So that's what I'm going to make my y min. My y max is going to be 4,000. But because I want to be able to see the intersection of that left and right side, I'm going to go a little bit above and go up to 5,000. Scaling it from 2,000 to 5,000, that's a range of 3,000 values. Maybe count it by 200s. And then hit graph. You'll know that you have an appropriate window. 1, if you see the intersection you're looking for. And 2, you see these clear, distinct tick marks on your X and Y axis. Just always think, what is my problem here? My problem's about money. So I know I'm not going to need the negatives. You could have started your Y values at 0 if you wanted to, but here we have an increase in the exponential function. We're never going to be below $2,000. So it's just kind of extra to be below it. That's why starting it at 2,000 is what I did here in our problem. Second, and then the trace key, option number 5. I'm going to get close to that intersection so that my calculator approximates it the way I want it to. And then enter 3 times following the prompts. Again, I should expect to get the same number I got algebraically. So if you're asked to solve this algebraically, you could always double check using the graph. You could also look at it using the table. If I go to second and then the graph key, I could see that between 11 and 12 years is where I go over the $4,000 mark. In our last question, we're going to look at creating a logarithmic model using regression. So after a major Category 4 hurricane, a power company provided the following information regarding the number of customers without power in the service area. So this is the information that we're given. We're going to find a logarithmic model for the data. We're going to let n be the number of customers in millions without power and x equal 1 be the day of the hurricane. So I'm going to open up Excel. Input value is day, output value is number without power, and that's in millions. And I'm going to enter in the information that I have on that table. Now remember, because this number is in millions, I need to rewrite what is given in my chart. Now I'm going to select all this information, go to Insert. We want to insert a scatter plot. And here's our information. Okay, so it has a logarithmic shape, but it's a negative logarithm. So remember when we talked about translations, that if the value in front of the logarithm is negative, it's going to flip that logarithm in the other direction. So I'm going to right click on any point there, add a trend line. Okay, we're going to change it to logarithmic, and we can see that not a bad approximation. Remember to display the equation and display the r squared value so we can see how close that approximation is. But we see that we have negative 1.464 and the natural log of x plus 2.4251. My r squared is 0.9758. So this is a pretty good model because remember, the closer r squared is to 1, the more accurate the approximation is going to be. Now the next question asks us to use the model to estimate the number of customers without power on day 2 and then at day 4, and how do these values compare with the data? So using my calculator, since that's more convenient for me, I have negative 1.464 times the natural log of 2 plus 2.4251. So on day 2, they're approximating 1.410, so about 1,410,000 people have no power. So on day 2 in my table here, I have 1.24. So again, not a super close approximation. It's off by about 200,000 people, but not terrible. Let's see what happens if we look at day 4, if it's a better approximation or a worse approximation as the data progresses. So on day 4, we get about 395,565. On day 4 of my data, I have 392,294. So this is now only off by around 3,000. So not as bad as the day 2 data. Okay, the last thing we're going to do is use the model to estimate numerically when there are fewer than 1,000 customers without power. So numerically means we're going to use the table. So into y equals is where I'm going to go. And again, I have negative 1.464, the natural log of x plus 2.4251. Second, and then the graph key. Okay, and looking at the table in our calculator, it looks like at about our data is approximating at day 5, there's about 60,000, 70,000-ish. So they're saying sometime between day 5 and day 6, we're going to get down to nobody being without power. So probably by that end of that week, around day 6 is when there's going to be under 1,000 people without power.